But I promised you to speak about weather research. I will present you two studies that for the first time included climate data and combined climate data with winter losses of honeybee colonies. Today we hear much about the influence of climate on our life, on, for example, forage crops. But what do we know about honeybees and honeybees and climate change? So I want to show you one slide, what is known and what can really be said, what has been scientifically investigated. And I must say, it's not that much. I mean, every one of you, of course, knows that there is plenty of ways how the climate and the weather could affect honeybees, but it's not very well studied, I must say. So there is a very classic work, I would say, done, I think, in the United Kingdom that showed the effect of weather factors, of course, on honeybee flight activity and colony weight gain. And the more sunny conditions you have, the more the bees can fly. And this is, of course, associated with inbrought nectar and pollen. But also the behavior, for example, of not only forager bees, but also nurse bees that stay in the hive all the time, that are not affected, for example, by rain outside, but also the behavior of nurse bees in the hive is affected by weather. When we think about varroa treatments, we must also say that temperature, and I must also add here, humidity, of course, has an effect on, for example, varroa control method using formic acid. And finally, from a very similar survey that we are doing in Coloss, the colleagues from, I think it's Luxembourg, Bayer et al., investigated the effect of different varroa control strategies and the role of weather conditions on honeybee winter colony losses, and they also found effects, not surprisingly. But I'm going to show you today two studies from real data sets, and both are based on Coloss monitoring data from Austria. The first one was published in 2017 and included 6 years of data on wintering mortality, and the second one was very recently published, including a 10-year data set, and both are, of course, available open access. So let's start with the first one, where we had this 6-year data set, and you can see on the right upper corner, we were using the data from 2008-9 winter to the 2013 and 14 winter. Collectively, the Austrian beekeepers participating in our study wintered 106,000 colonies there. And we used the integrated nowcast data set from the Austrian Meteorological Society, calculated a 5 by 5 kilometer grid over Austria in 2 different temporal resolutions. And I'm basically going to show you the 1 month resolution here for this publication. And statistics, we did a nearest neighbor model with colony loss data to see what can we say. And if I say we're using a data set, what can we obtain from this data set? It's the precipitation. So if there was rain or snowfall, and that's the sum of precipitation reading, like there was 5 liters per square meter, for example. Very important, you will see, is the temperature, and we are differentiating between different temperature measurements. One is the minimum temperature that you usually have early in the morning, the maximum temperature that you usually have in the afternoon, and of course there's also a mean temperature that describes the full day. Radiation is giving us information if if the sun was shining or if it was cloudy on that day. And the zonal and meridional wind speeds were also included in the model, but I can already say now those had the least effect on honeybee colony mortality. So let me show you how this looks like. So we have here Austria and all the operations that participated in those 6 years, and we plotted them so we know exactly the location, and they fall within one of those 5 by 5 kilometer grids. And of those 5 by 5 kilometer grids, we know what the temperature was, how much rainfall we had there, etc., etc. And already to show you, the mortality can be seen here. If it's red, that means this is operations with very high mortality, and this is accumulated for 6 years, as I said here. And blue means rather low mortalities. And we're gonna use these mortalities always with the weather conditions the full year before. This is just one example. This is, for example, the precipitation, the rainfall in April 2014. And we did look if the rainfall in April 2014 had an effect of the honeybee overwintering for the winter 2014 and 15. And what you can see here, we have very dry areas in the north and in the east of the country, but in the center of Austria, you see there is really lots of rainfall here in this example here in April. But let's go away from rainfall. I just shown you this because you could really see nice variation in here, but let's focus more on temperature. And I said that we are having several temperature measurements, and one is the average maximum temperature measured in degrees Celsius, and that's what you can see on the x-axis here. And this is the average maximum temperature for the month of September. So it's the September before the winter. And on the y-axis, you can see the colony mortality percentage. And this is from 0, no honeybee colonies lost, up to 100. And the size of the bubbles gives us an idea of the operation size. The bigger the bubble is, the bigger is the operation size. The very small dots, this is only very small operation sizes. And also we did include, but that's not of importance for our understanding now, the longitude where in Austria we could find those operations. And what we are doing now is we are having situations, for example, where in September we had average maximum temperature of about 15 degrees Celsius, which is a really cool September. And on the other extreme, we have some situations in Austria in some years and in some regions where we have average maximum temperatures of 30 degrees, which is very warm Septembers. And what we are doing next is we are dividing this data set into a lower half and into an upper half. And we are calculating the average maximum temperature for the lower half and the average maximum temperature for the upper half, plus the colony mortality percentage for the lower half and for the upper half. And here you need to look closely now. I'm going to show you those values. It's those yellow points that I'm animating now. So you see the lower half, we have September average maximum temperatures of below 25 degrees Celsius. And if you now follow to the left side, what mortality rate this lower half has, we have a mortality rate of about 17%. In contrast, the upper half has average maximum temperatures in September of 20 degrees Celsius, almost 30 degrees Celsius, about 28 degrees Celsius, I would say here. And if you look then on the left, and I'm going to animate, and I'm going to animate again, look at the right dot, and then follow the right dot to the y-axis label, and then you can see that we have 20% honeybee colony loss rate for this. So we have differences in the mortality rates for those locations where we have lower temperatures and where we have higher temperatures. And we did this, of course, not only for April rainfall or September temperature, like I've shown you here. We did this for all the climate predictors that I've shown you before. And what you can see here is below you see the months prior to loss count, which is March, April, May, June, July, August, September, October, November, December, January, and February. And on the left, you can read the potential climate predictors. And if I start from below, you see U and V is the east-west and north-south winds, to say it very simple. And you can see that those winds have a rather, they are not very color intensive. Above you can see the T values, and we have T minus minus, which is the minimum temperature in a month, April, for example. T is the average temperature of the month, April, of any given month that you can see here. P is the precipitation, and R is the radiation. And what the coloring of this plot shows us if there are differences between the upper half and the lower half. Let's go back to this example. I've shown you here that the preceding September average maximum temperature had a different colony mortality percentage from the lower half, which was lower than the upper half. We are now calculating the difference of this colony mortality. And this is what we are showing here. So if the field is colored white, it means there is no difference from upper half and lower half. It does not make any difference if there is more wind or less wind. That's what we can see here. But if we look for our September, I'm not sure if I can show you that. No, I'm sorry, I don't have a. But if you look at the September T plus value, you will see a very dark red field. And this dark red field means that there is a really great difference between the upper and lower half. And in our situation, it means, because it is red, it means the warmer September is, the higher the mortality is. As a contrast, I can show you that if November is really rainy, it means that's very blue. So you need to look at P and N for November, for example, and it's dark blue. And that means if there is lots of rain in November, the mortality is lower. That's why it's blue. I know this is really complicated. And now one even more complicated graph, and then we will have much simpler graphs. So we plotted everything on this diagram. You can see on the x-axis the annual temperature, and the annual temperature is really such a rough estimate. This is where you would compare Denmark and Austria and Spain, right? That's the annual average temperature. And on the y-axis we have the annual total precipitation in millimeters, and each cross in this graph indicates a beekeeping operation and the situation that the beekeeping operation experienced. And we calculated the chance for mortality based on our data set. We calculated in this model that I mentioned that the risk for colony losses. And what you can actually see for the situation of Austria is red means high mortalities. And where do we see the red area? That's where it's very warm and with less precipitation. So very hot and dry conditions in Austria are associated with higher mortality. I must tell you that, of course, this is based on geographic information, and weather never comes alone, because it's a difference in Austria if we are at 1000 meters above sea level or if we are down here at 400 meters above sea level. And it's not only the climate that is different in those two different locations, it's also, of course, the land use. So you can imagine that in those lower regions, we have completely different forage sources, we have completely different crops, for example. We have a higher density of crops, whereas in the higher regions where it's cooler and more rainy, we have more forests, more natural areas, and so on. So climate never comes alone. It always is associated also with land use. That's what I wanted to say here. Next study already included a 10-year data set with 260,000 winterings of honeybee colonies. And what we did was something actually very simple, in contrast to the very complex modeling that we did here. We did fit simple and multiple linear regression models to our data set. Again, we were using the Inca data set on climate, but here we focused only on temperature and precipitation, as we found out that these are the two most important factors. And we did not work on annual or daily, we did not work on annual or monthly resolution, as I've shown you before, but we were working on daily temporal resolution. And we formulated, before we made this research, 4 hypotheses. And for this hypothesis, I again spoke to beekeepers. Hey, what do you think is a good weather situation for wintering honeybees, and what is a bad situation? Or in general, what's good weather for honeybees and what's not so good weather for honeybees? And we were testing the 4 most promising hypotheses. We had some others which we did not follow up on, but we formulated those 4 hypotheses, and I'm gonna show you all those 4 hypotheses now. The first one is, we want that our bees during summer can forage optimally. What do we need for good foraging? We need temperatures, mean temperatures of above 10 degrees Celsius and no rain. That's a very strict criterion, because actually it could rain during the night when the bees are not flying out anyway, but in our data set we cannot differentiate at which time of the day the rain is falling. So we said, okay, let's better take completely dry days. So those days describe really good foraging conditions. You can imagine the bees are flying out, and we are counting the number of those days in the time frame between 1st of March and last of October. And this is a little bit of advertisement. If you want to go to Austria for a holiday, and if you want to have it sunny and not rainy, you should go to the very eastern part of Austria, because here you can see the dark green shadings, and this means we have more than 100 or even more than 140 days that fulfill our criteria, that there is no rain and it's warm, right? There is less such days in the north of Austria and in the center of Austria again, because there is the high mountains. And what is gray here and in the following maps is areas above 1,200 meters sea level, because we said, okay, there we have really extreme weather, and it doesn't make sense to include that into our calculation, because there is very rarely beekeeping above 1,200 meters. I don't say it doesn't exist, but I say it doesn't really make up much of the Austrian beekeeping. So we masked out in all the following graphs those areas above 1,200 meters sea level, and we also did not include those extreme weather in our calculations. What we take home here is, in the east of Austria, we have more optimal foraging weather than, for example, in the west or in the north of Austria. And now, again, we have this 10-year data set on honeybee colony mortality. We can correlate this with the winter mortality. And I must say, that's a little bit a trick that the climate researchers are doing. They're not working with the absolute data, but they are calculating indicator anomalies. Because then we can compare if it's warmer in the southern warm regions compared to what it used to be, and the reference data set for this is 1981 to 2010. Because if it has 35 degrees in the lower regions, that's something different if it has 35 degrees in the higher regions. Then you have a higher indicator anomaly. And what you can see here in the results on the right side is, indeed, the higher this indicator is, the lower the losses are. And this was, well, it's never a perfect fit, but we are working with big data, and we clearly found that the p-value is very, very low. That means we really found a relationship here. The more optimal foraging weather during the flowering period we can measure in Austria, the lower are the colony losses. And we can explain this with the fact that if the bees are always flying and foraging, they have a short renewal period, they are very vital, they are less susceptible to different pathogens, diseases, for example. They have lots of food flow, and it's always good if the colony always has food income, and they really build up strong colonies during summer. And again, those strong colonies, they have higher chances to survive the winter. How about autumn? Late autumn is defined in meteorology as between 15 October and 15 December. So just have a look outside your window and you know what late autumn is. And we wanted to see if any cold spells in late autumn correspond with our winter mortality. And a cold spell we defined as a day with a minimum temperature below -5 degrees Celsius, and each day of the period has a mean temperature of at most 3 degrees Celsius. We just had that the last few days here. If the average daily minimum temperature of the next period exceeds -3 degrees Celsius, the cold spell is stopped. So what we are doing now is we are counting the total number of days in cold spells in the period 15 October to 15 December and the maximum duration of those cold spells. And we are summing this up per year. And again, I can show you where you want to go if you want to have it really cold in late autumn. Then you should go to the mountains. So you can see an opposite picture here. You can see that on the northeast of the country, you don't have many of those cold spells, but the more you go to the central country where the Alps are, where the mountains are, the more of those cold spells you have. And this is including now the number of days in these cold spells and also the maximum duration of cold spells. And what you can see on the right is, again, the more of those cold spells you have, the lower is the mortality of winter loss. And before I said we want to have nice warm weather and dry weather in summer or during the foraging, but we believe that those cold spells in late autumn, they trigger the bees to shift to wintering behavior, so that they are not foraging anymore, that they're stopping breeding, and this seems to be good for the winter success. So we want warm summer for our bees, and we want cold late autumn for our bees. Next one, the next two actually directly impact the wintering behavior. And first of all, we were asking about mild winter weather, and later on I'm going to show you that we also were looking for cold winter weather. But what do we mean with mild winter weather? Imagine that you have a really cold week in winter, and then you have one day that has 6 or 7 degrees Celsius plus, maybe some sunshine. There is no snowfall, no rain, yeah, because it's sunshine. And then you visit your colonies, and then you might see that the bees are flying out and defecating and cleaning, making cleaning flights. And beekeepers told me, hey, Robert, it's good if sometimes we have those mild winter weather days. And we defined mild winter weather as some periods that allow our bees to defecate, but we didn't know how often those should occur. And we were playing around with the data set, and we came up with something very strange to you, maybe for when you hear it first. We were counting the number of 9-day moving windows in January and February in which favorable conditions for hygiene flights occur. But a window is only counted if it contains at least 2 days with a maximum temperature of at least 5 degrees Celsius, and again, no rainfall or snowfall. To show you this. This is, let's say, 1st of January. We did it for January and February, and we are counting 9 days. And we have very cold weather indicated by the blue color of the calendar days. And we are counting now 9 days. We find 1 day with mild winter weather, but the condition is not fulfilled because we said it should be 2 days with mild winter weather. We did play around a lot with lots of things, but what I'm going to show you now is it worked best with 2 out of 9 days mild winter weather conditions. Here, 1 day with mild winter weather condition not fulfilled. And I said we were working with moving windows. Now I'm moving the window. You see, I still count only 1 day in my green window here, but the next one, wow, in this time window, I actually have 2 days with mild winter weather, so I can count it. Next one, again, of course, again, and so on and so on. We can calculate the percentage, how often such windows with mild winter weather occur, and you can see that this is most often happening in the south and in the east of Austria. You almost don't have such days in the mountain regions. And this again negatively correlates with winter colony mortality. And the negative correlation here means the more of those mild winter weather days we have, the lower the honeybee colony losses are during that winter. I'm going to show you the vice versa of this. How about the cold spells in winter? And here again, we are counting periods of at least 10 consecutive days in January or February, where we have a maximum temperature of below 2 degrees Celsius. Those is those really cold winter days. And a cold spell is defined as 10 days of really cold weather. If the average daily mean temperature exceeds 0 degrees Celsius, we interrupt it. So again, this indicator consists of 2 variables, the total number of days in cold spells and the maximum duration of cold spells per year. And here we have a vice versa of what I've shown you before. If you remember, we had the most days with mild winter weather in the southern and in the eastern region of Austria, and here we have the fewest cold spells in winter. But in the north of Austria, we have the most cold spells in winter, indicated by those dark blue shadings. And here we have a positive correlation. Positive correlation means the more of those cold spells in winter we identify, the higher is the winter mortality. And to sum up all four hypotheses, this is the strongest effect that we found here. And actually, you could have also seen that on the first article that I've shown you, we also found there that January and February cold spells are negatively affecting the wintering of honeybee colonies. Let's build now a perfect year for bees. Let's focus on the last two parameters regarding the winter that I just shown you. So it's better if January and February has, for Austrian bees, maybe 2 warm days within this 9-day windows. Why? Because the winter cluster, can change comms to connect to the food stores, and I'm going to show you that here. You of course know that the bees, they're consuming the food, and if it's very cold, they don't want to cross one comb to come to the next honeycomb, but they can do that if it's not too cold in winter. And second, I already mentioned that, if there is a nice warm day, the bees can fly out and make cleaning flights, which is also good for the survival. So all the four hypotheses that I've shown you were validated, and we can summarize that the indicator maximum duration of the extreme cold spells in January, February, and March was determined as the most significant weather-related factor. And I'm going to say something about the 10 to 20% in the next slide, because both studies showed us that approximately 10 to 20% of the winter mortality variability can be explained by the analyzed weather conditions. And if I say here 10 to 20%, that means if I told you before that we have an average in Austria 16% loss rate of honeybee colonies, we are speaking about 10 to 20% of those 16 percentage points that we can explain with weather. That's 1.6 to 3.2% roughly. Because we already know there is other factors. I've shown you already. Varroa mite, Varroa treatment, etc. But the weather can also explain some parts of the winter mortality. Both studies also showed that even the weather before the winter determines the wintering outcome, and I think that here are further studies needed, including also the best beekeeping management practices, also in regard to climate change, because I think that beekeeping will change, but we don't know much about how our bees will behave. So details are difficult to project, but bees will somehow be affected, but maybe primarily because pests and pathogens are also affected. And there was a recent article that demonstrated for Poland, for example, that Varroa is favored by warm spring and autumn conditions. Again, something that corresponds with our data, but I did not interpret it now in the relation to Varroa, but I pretty much believe that also Varroa has something to do with that. If the bee colony has more breeding cycles, also the Varroa mite has more breeding cycles and they can reproduce. Also for other pathogens, it was shown that warmer conditions are favoring the pathogenicity of different pathogens. So it will also make disease control maybe more complicated. Finally, there might also be effects on the forage sources. We were not speaking about those effects of forage sources so far, but of course you can imagine that if the vegetation dramatically changes, also our bees are affected by this. Quickly, some other outcomes from the Coloss research for practical beekeeping. we were speaking about Varroa treatment, and I want to show you our latest investigation. We were interested in spatial clusters of Varroa destructor control strategies in Europe. Our question is, what do European beekeepers apply to fight the Varroa mites? And there are some few previous studies, mostly from the United States. And the study on the right lower corner is a global study, but with very few answers from outside Europe. And all over Europe, they have about 300 to 400 answers. So they don't differentiate between countries, but they just in general tell us what beekeepers do in regard on honeybee disease management and control. So they are not only including Varroa control methods, but also control methods, for example, for European and American foul brood. So from the Coloss data set, we are asking beekeepers, when do you apply which treatment? And what you can see here is a list of, I think it's 36 countries. I'm not 100% sure now. No, it's 30 countries, I think. And we can see that, for example, let's start with Austria. We have 1,453 respondents. 78.1% are doing Varroa monitoring. 53%, so every second beekeeper is doing drone brood removal. Some beekeepers do hyperthermia. Some beekeepers do biotechnical methods, but the majority are doing FA, stands for formic acid. The majority are doing formic acid treatments, and here the formic acid long-term treatment is favored. If you look at Denmark, we see that you are one of the champions with 85% of oxalic acid trickling. I think you are the heaviest users of oxalic acid trickling in Europe. But also formic acid treatments I can see here are done very often. Thymol treatments I can see here, and very few flumetrine, for example. Treatments. Let's go to your neighbor. This is Germany, and you can see that Germany is quite similar. They only have 60% of oxalic acid treatments. Of oxalic acid trickling treatments. The Germans, they prefer more to sublimate the oxalic acid because they have 13% in contrast to the 2.9% that you find in Denmark. But let's go now to a completely different situation. This is France, and I know you cannot see that very well. Just have a look at the column where it says Amy strip, that is Amitraz in strips, and you can see that the French, they are not using the oxalic acid trickling like the Danish do, but they're using Amitraz in strips. So we're learning here, in each country, beekeepers are doing something different to control the Varroa mite. This data we put together into an analysis that is called the Correspondence Analysis, and there we saw, we can identify 3 different clusters that are now arranged on the similarity of Varroa control strategies. And I'm going to show you that on a map. So you can see here, for example, first of all, this is based on 28,000 beekeepers that manage 500,000 colonies in 30 countries. Here I got it now. And we can see that the British Islands, France, Spain, and Portugal, they form a cluster on their own. Whereas the Scandinavian countries plus Germany, Denmark, Netherlands, Belgium, Austria, down to even Bulgaria, Greece, and Italy, they are using different methods. And I can tell you, this is the formic acid countries. And again, the Eastern European countries, they use something else. But what are they using? That's shown here. Cluster 1, which was France, Spain, and the British Islands, they are mostly characterized by application of Amitraz in strips. And you can see that this is mainly done in the period of August to October. Whereas the cluster 2, which is where Denmark belongs to, is characterized by formic acid usage from July on, and the cluster 3, which is the Eastern European countries, is characterized also by the use of amitraz, but not in the form of strips in this case, but as aerosol or fumigation. So these are not the most prevalent Varroa control strategies, but these are the most different control options that I show you here. Oxalic acid trickling, for example, is not mentioned here because that's pretty much similar among those 3 clusters, and I already said the Danes, you are the champions in applying oxalic acid trickling. That was my presentation. I thank you very much, and I'm happy to answer your questions.